Let's now learn how to derive the local stiffness matrix of a truss element. So we discretize a truss structure into its elements, and a typical truss bar is something like this with length L, and we have a local coordinate system which we show with blue here with the hat on top of X to show that this is local. And as we said previously, only longitudinal forces could be applied to a single truss element. We discretized it and we drew the free body diagram for a truss element. We showed the elements in circle and the nodes at the two ends of the element with just numbers like that. And then we said that the local nodal forces and local nodal displacements are always in the positive x direction for the element free body diagram for both nodes. So we have F1x1 and D1x1 with the hats, which show that this is the local nodal force in the x direction at node 1 for element 1, and this is local nodal displacement of node 1 in x direction attached to element 1, and this is basically the same thing for node 2. And then we drew the free body diagrams of the nodes separately. So we said that the local nodal forces are always in the opposite direction of what they are in the free body diagram of the element. So because here they were in the positive direction, in the free body diagrams of the elements of the nodes, they are in the negative x direction. But the external forces are assumed to be in a direction that would put the element in tension. So because the node 2 is there and node 1 is in here, if we apply a force like that, and the force is applied to that in that direction, in the positive x direction, and this one is in the negative x direction, we would put this bar in tension, and that's how we show them here in the free body diagrams of the nodes. From these free body diagrams, we also found that F1x1 is negative x or negative f, and F2x1 is equal to positive f. And that's from the equilibrium equations that we wrote for the nodes separately previously in the stiffness matrix of a spring. Now before we move on, we need to define a displacement function. Again, the displacement function is an assumed solution for the displacements of the bar or the truss element here. So because we only have 1 degree of freedom per node, so we have 2 degrees of freedom per element, we choose a simple first order polynomial which has two constants, C1 and C2. And with the two boundary conditions at the two ends of the truss element, we can find the C1 and C2. So if I go back here, the displacement of node 2 is D2x1, and the displacement of node 1 is D1x1, as we assumed in our free body diagram. So we can say that u at x equals 0 is equal to d1x, which is the displacement at node 1. And if you put that in this equation, if we put 0 instead of x, we'll have c1 times 0, which would make this term to go to 0. So which means d1x is equal to c2, as we've shown in here. The second boundary condition says that the other end of the truss element, when x is equal to L, the displacement would be d2x1. And now we have C1 times L plus D1x, which we got from there, is equal to D2x1. And then we found out that C1 was D2x1 minus D1x1 divided by L. And using those, we found this equation for the displacement function. And then we arrange the displacement function like that to have them as D1x1 and D2x1 separately. And we found that this would be the equation 1 minus x hat over L times d1x1 plus x hat over L times d2x1 becomes the displacement function. And this has the advantage to be written in a matrix format like this. So u of x hat is equal to this 1 by 2 row matrix. 1 minus x hat over L is the coefficient of d1x1, and x hat over L is the coefficient of d2x1. So if we write that here and multiply it by this 2 by 1 vector, the first element of this vector is d1x1, which is from here, and the second element is d2x1, which is from here, it gives us a 1 by 1 scalar, which is basically the displacement at any node or any location along the length of the bar. Now we know that, we come to the Hooke's law. This stress equals Young's modulus times strain, and stress was basically Fx over A, and strain is delta L over L. Another way to define epsilon or strain is to say it's equal to the gradient of displacement with respect to x, or the distance. So here we define epsilon as a gradient of ux over x, and we had the equation for the displacement function from before, which is written here. Basically this is u of x hat, and if you take derivative of this equation with respect to x hat, we will end up with d2x1 minus d1x1 over L, and that would give us the strain for each bar in the truss. Now we replace the sigma with F over A. E is constant, we leave it there, and we replace epsilon with this equation we found in here. This would be our new equation, and if we rearrange it, we will end up with this final equation. Now, this is force, this is displacement, it could be delta, it could be delta x, and this is the stiffness of the truss element that we found for a single truss element. Now, using that equation and using the information we found from equilibrium per node, that we had f1x is equal to minus f and f2x1 is equal to f, we can move on and write these equations. So minus f1x1, replace it there, ea over L times d2x1 minus d1x1, and f2x1 is equal to ea over L d2x1 minus d1x1. We rearrange this first equation to bring the minus sign to the other side, to the right hand side. So it would be f1x1 is equal to ea over L times d1x1 minus d2x1. So if you look at this and this, the only thing that is different between them is the sign. This would be, if this is positive, then this would be negative. Now, using these two equations, we can create a vector of forces. So this is the vector of nodal forces. Let me write this down. And this one is the vector of nodal displacements. So, and what we have in here is going to be the stiffness matrix, or the local stiffness matrix of a single truss element. So we show it like here with a hat on top of the K to show that this is local. EA over L is usually constant, and these elements of the matrix, the 4x4 matrix, becomes, or 2x2, I'm sorry, it's a 2x2 matrix, becomes 1 minus 1 minus 1, 1. And the reason for that is f1x1 or f1x1 is equal to EA over L. So look at here, EA over L, d1x1 minus d2x1. So we want to multiply this dix1, d1x1 by 1 and d2x1 by minus 1. So that's why we write that there. And for the f2x1, it becomes positive for d2x1 and negative for d1x1. So put the negative here to multiply by that, and the positive one there to multiply by this. And as a result, we get a 2x2 stiffness matrix for the local stiffness matrix of a single truss element. And the reason we have a 2x2 is that we have 2 nodes per element, and we have 1 degree of freedom per node. So if we multiply that, we will have 2, which determines the order of the local stiffness matrix for a truss element.